thank you very much. So good afternoon, everybody. Just one lady and gentleman. I would like to give a speech about digital predistortion using NI AWR. So actually, currently I'm from Brno University of Technology, and I am following project which started led by Geneviève Baudoin, who is from esiee Paris. So thank you for the opportunity being here. First of all, I would like to introduce a few words about our institution. So as you may see, we have several research groups. I belong to the radio frequency applications or mobile communications group, and we have several foundations to support our work. So more or less, I work with digital predistorters. Geneviève and her team is from Paris, from esiee.fr laboratory, and she has as well a very long, I would say, history dealing with digital predistorters, and not only. So for those who are not familiar with digital predistorters, I would like to say a few generalities. For those who know this stuff, I apologize in advance. So why we need actually some kind of predistorters? So we know that coming with, I would say, more complex modulations, different behavior may appear, and it's mainly due to high PAPRs. Like OFDM, we know it has high PAPR, so the efficiency of PA may decrease. So we need to set up a big back-off, which would degrade the efficiency in general. There can be different things happening in PA. We know memory effects. So this is a never-ending story between PA designers and signal processing guys. So PA designer say usually there are no memory effects coming from the PA design. Signal processing guys say it's memory effect coming from your design. So let's agree and call it memory effects in general. There can be, of course, some distortion in EVM, so everyone knows what it is. And as well, we can see some spectral regrowth. So we call this kind of metric ACPR, or we can call it. There can be different. So there are actually different methods for improving linearity or efficiency. So on the one side, the efficiency can be improved, for instance, by using different architectures, such as Doherty, or we can actually increase, or I would say improve linearity, which where we can use different techniques, such as feedback or predistortion. And today, I am going to mainly speak about digital predistortion. So actually, there can be different placements of predistorters itself. So predistorter can be actually placed, I would say on IF or on RF or on baseband. So our digital predistorter more or less work in baseband. So I would be mainly speaking about that. So what is a digital predistorter? Digital predistorter is actually a device that is being placed in front of a PA, and it is trying to inverse its characteristic. So the predistorter should have feedback information, I would say, in order to calculate some coefficients, which will be then used for inverting the characteristic of PA. We can distinguish between different DPD structures. So we can have some quasi-static models, or the, I would say, first one were just purely static. So we can see there is a low complexity, but we more or less cannot correct memory effects. Or we can have dynamic models, which more or less are derived from Volterra series. These are the most popular ones. But we can use as well neural networks or some kind of multi-stage, I would say, combination of filters and some polynomials, for example. The problem of dynamical models is, of course, the complexity of identifying the coefficients. So this is a short overview. So among the first predistorter is, of course, the lookup table. So lookup table was more or less used for no, as a static DPD. We know that it can be enhanced to dynamic DPD, so it's very simple. But in case we would like to have, I would say, very good lookup table predistorter, which has possibility to correct even some memory effects and so on, the complexity will increase. So it's not very useful. But in comparison with others, it can be beneficial, for instance, in case of simplicity and so on. So it can be used as a very simple predistorter. About multistage models, so first, DPD models, I would say, dynamic or quasi-static, were proposed by this Venard or Hammerstein architecture. So what it say? It says that we can actually divide between a static part and dynamic part. So dynamic part can be actually this filter. Static part can be nonlinearity. So they are, I would say, more or less similar, just switched the order of the boxes. And of course, then there can be combination of, I would say, each others. So among the most common used series derived from Volterra series, we speak about memory polynomials. So memory polynomials, if we look, they have something that is called as a nonlinear order, and which is K in this case, and M, which is called as memory order. So if we look inside, K actually is in the power series, and M is, or in this case, L index, is actually shifting the signal over each other. And we can see in here is some kind of absolute value. So the reason is we are calculating with complex numbers. So if we go from passband to baseband, we should include as well the magnitude of signal. More advanced model is, sorry, this is a mistake. This should be a dynamic deviation reduction second order proposed by Anding Zhu and others. As we may see, this model incorporates much more complex behavior. So on the one hand, memory polynomial could be sufficient for, I would say, some simple nonlinearities, but it cannot correct everything. So this DDR, how we call it, could be used for some, I would say, more complex behavior correction. There is as well generalized memory polynomial, we call it GMP. So if we look at the model, it actually is polynomial model. So this is the diagonal of a Volterra series with upper and lower, I would say, terms under and lower diagonal. So lower term actually includes delay terms, upper term, or this one term includes advance of signals. So this model tends to be very interesting because it can correct a lot of nonlinearities. Unfortunately, there are a lot of terms that should be set up, so it's not very easy to estimate all the terms. And from the general experience, higher order does not mean always better predistortion. Example of how neural networks can be used for a predistorter. So of course, we can have some kind of neural network which is processing real and imaginary samples. We have delay, we have advance, so more or less it's GMP. But the problem with neural networks is their calculation of all the weights. So on one hand, these networks tend to be very interesting in terms of linearization, but calculation is still a problem. So few parameters that we use for evaluating DPD. So as I said, ACPR. So ACPR more or less is power, I would say, in the adjacent channel. So it's kind of ratio between the main channel and adjacent channel. We as well can evaluate EVM, which is known. It's actually error between, I would say, expected symbol and the symbol that is measured. And we more or less use NMSE as a criteria of error. So it's just a mean square error, which is normalized by its input. This is an example of trying to linearize some kind of PA. So as we may see, it was a PA for digital television broadcasting. What we can see, so the blue is, I would say, memory polynomial. So on the lower axis, there is a nonlinear order k. So we may see that increasing the order does not always lead to better results. So there is a certain edge after which we don't improve anymore. And the same holds for memory. So there have been proposed several methods actually how to estimate the DPD orders. So we call it structures. So among them, there can be some kind of analytical methods or some kind of, I would say, heuristic using, for instance, genetic algorithm or hill climb method. I think it was presented in London last year, this kind of method as well. Or there can be some kind of, I would say, more or less analytical method which can actually try to calculate the orders based on significance of kernels. So how to actually identify DPD? So one approach is being called direct learning approach. So direct learning approach actually is taking a feedback of a PA, is trying to estimate the coefficients, and then it is trying to apply these coefficients to DPD. This method needs to use some kind of, I would say, nonlinear approaches, because we are actually trying to linearize power amplifier, which is nonlinear. So if we do it directly like this, then we have a nonlinear problem. So we should use tools used for nonlinear optimization. On the other hand, there is a very popular approach, indirect learning approach. So if we look, there is our predistortor, and we use a postdistortor. And in case we are trying to minimize error between predistortor and postdistortor, then our PA is masked behind the postdistortor. Therefore, it's a linear approach. So we may use methods for actually matrix inversion, which is used, we call it least squares, which is used for calculating the coefficients. So in this case, it's no more nonlinear problem, and we can use standard tools, which is good. So this is example actually how such least squares can be derived. I think we don't need to go through. It's a standard least square, so expect we have our problem. We are trying to find the B coefficients. So if we set up criteria, which is trying to minimize error between two vectors, then we can actually do derivation, which is here, set it to 0, and we can calculate easily our B coefficients. So this is a standard tool. But I have here small remarks. Never invert matrix directly. It can cause problems. Because we, for instance, may use QR decomposition or something which is, I would say, iterative way. Because when we invert matrix directly, we can have numerical instabilities. So just a small remark. So this was method which is able to actually calculate a solution on vectors. But there are as well methods which are, I would say, semi-adaptive or adaptive. So by adaptiveness, I mean it can adjust the coefficients based on error of the previous calculation. So, or on the previous data. So in here, this is called damped Newton. So we may see it's standard Newton method, which is updating the past coefficient by some kind of sensitivity vector multiplied by error. So this is widely used. Then we can use, of course, LMS or RLS. The difference between these three is that the first one more or less may operate with vector and matrices. The other two can calculate, I would say, online. So they can derive the calculation or the coefficients sample by sample. So it's always a question if the real-time implementation is needed. We know that there can be effects actually which are not very fast. For instance, thermal effects, they don't appear from nowhere. So I would say it's slow behavior. So as we can see, it's always question if to update coefficients, I would say slowly or fast, or do we need the calculation? For calculation, we may use FPGAs or GPU and other stuff. For identification of the DPD model, there is always a calculation over large matrices, so this has to be considered. And of course, we should avoid numerical instability problems. For direct path of real-time DPD, we need to do some kind of multiplications and additions, but this is a general thumb rule which says we need to have 5 to 7 times the Shannon frequency of our sampler in order to predistort the signal. The same is applied for a feedback path. So you may imagine for 5G, where 10 gigabits per second is expected, to have a feedback path with 7 times of the sampling frequency might be an issue. So, and of course, when having a DPD, the DPD is not alone inside such systems. There might be, for instance, crest factor reduction and so on. So we provide a DPD inside AWR in order to help designers, I would say, to make DPD-friendly PA. So what I mean by that, actually we can, as a designers, we can, with our tool, try to optimize the design and see if it's sensitive to predistorter or not. So by that I mean the question is if the design should be very precise, or do I have some space for designing the PA, I would say, more low cost. So we had a project, or we have still project with AWR, and the goal was to integrate DPD inside their tool. So it can actually help, as I said, PA design, but it can as well help people who design DPD. And of course, it can help to, I would say, set some kind of FPGA implementation. So this is example from NI. As what you can see here is we have a QAM modulator. We have a power amplifier, which is a circuit. The circuit is very simple, but it's a circuit level. So this is just a gain. I put this gain here. It's linear gain to see if the feedback path behave correctly. So I was playing with that. And in here, we have our digital predistorter, which has, I would say, several options. And the top branch is there just for comparison with predistorted signal. So we are trying to compare PA without predistortion with PA which has predistorter. So I was speaking about it. And here is the comparison. So the pink signal is a transmitted signal, which is then amplified, and we can see output spectra of our PA without predistorter. And the blue curve represents signal with predistorter. So this is just an example what can be achieved with DPD in the system. The DPD actually has several options that can be set. So you can see there are some orders to be set up. So this is the reason why I was mentioning memory polynomials, dynamic deviation reduction second order, and GMP models. So we can play with the orders. And of course, we can set between different solvers that we have implemented. So least squares is a solver which calculates the solution only at the beginning, and then it does not update. Next, there is the damped Newton, which can be used for some kind of dynamic update of coefficients. And the last one is dynamic. It's damped Newton with step reduction. So this algorithm, after a few iterations, just reduce its step. So it allows us to find faster the initial solution, and then it decreases its sensitivity. There is a next example. So we took the PA. It's a 1 watt X-band PA provided by AWR. It is the one with bonfires. We may see the transistors. It's two-stage PA. And of course, the same circuit, and we can see one signal which is not predistorted and one with applied predistortion. So it is easy. Yeah. So then I would like to actually show you a small demo how it works, because this presentation does not have to be sufficient enough. So now I apologize to everyone recording the presentations, and I'll try to switch to my PC. Okay. All right. So this is the circuit that I was describing in the beginning. So if we look inside, this is the model of PA. So if we look inside, it's a circuit board, or some kind of circuit simulation. So if we look at the spectrum, I first have the solver off, so I will try to turn it on to show you an example. So in this case, again, the blue is with predistortor. The, I would say, red or brown is without predistortor and transmitted signal. So now I try to turn on the solver. So the simulation is running. I'm trying to turn on the solver, and we are predistorting. The reason of oscillation is because I have set up very small buffer for the calculation. So in each run, the PA/PR of signal changes a little bit. So if I set up longer buffer, I can avoid this kind of behavior. Then, of course, we may try to switch to damped Newton. Oops. And we can see it works. But if I stop the simulation and I tune a bit our sensitivity to another solution, so I will put here like this value. So now the predistortor should be able should update its coefficients slower. So if I turn it on, you may see that it needs few iterations actually to calculate the solution. Yeah, it goes very slowly and slowly, but it's doing something. So it's this is actually a tool that I would say PA designers might use seamlessly without speaking to signal processing guys. So this was the first example. Then this is the actually MMIC on 10 gigahertz, 1 watt. So again, we have two circuits to compare. The circuit here has bonfires included, so I will just turn it on and show you what it does. So we may see that with this setup, we are not able to achieve, I would say, extremely good predistortor, or extremely good behavior of the predistortor, but I think I broke something. Yeah. Yeah, I did something wrong, but it's okay. No, it's so anyway. I have a. Let's go back to our previous predistortor. This crashed due to my fault, so I'm sorry for that. But I would like to show you something different. If I run the simulation, and I will just speed it up. Okay, I'll run the simulation. So the power amplifier has a bias point. So I can, during the simulation, I can tune the bias point. So now we have 2.59 volts as a bias voltage. So let's say I don't know anything about design, and I increase it to 3.5 volts. So we may see that the DPD is actually able still to compensate. What is obvious, the behavior of uncompensated PA is not good, but we may see the DPD works. And of course, if we would like, we may tune the orders of the DPD simply by clicking. We would like to tune it. So there is one more slider. So if I decrease it, if I decrease the order too much, so let's say it's order 2, we may see that it's not really able to compensate. So the designer has options to play with our tool. So thank you very much for this opportunity, and if you have questions, go ahead.